Hello everyone, this is Dr. Zach. Today we're going to discuss the concavity of a graph and the inflection points of a graph. Let's get started. So as you were trying the lesson preview today, what should have stuck out to you is that the particle was speeding up on 1, 3, and that it was stopped at t equals 1 and t equals 3. Now what do we know when we say the particle is speeding up? We know that the velocity and the acceleration have the same sign. Then when you look at your acceleration graph, perhaps you made a sign chart to help figure out what was going on. We place 1 and 3 in the sign chart. Maybe you consider your acceleration as negative, then positive, and then negative. Now the reason we put 1 and 3 in there is because that is where your particle was stopped. Now if the particle was stopped, that's actually referring to your velocity. So we know the velocity is 0 at 1 and 3. All right, so the velocity is 0. The signs are the same for the acceleration and the velocity. So the velocity graph is above the axis. So perhaps it looks like what I've drawn. Now, the last thing perhaps you should consider is the acceleration graph is a quadratic, which means your velocity graph is most likely a cubic. Does it have to be what I've drawn? No, but as long as you get some sort of cubic shape drawn, you should be able to answer whether or not A, B, C, or D is your best choice. As you recall, the first derivative of a particle motion problem had to do with velocity. The second derivative has to do with acceleration. Now, just thinking about the graph of a function, the second derivative will give us details about the concavity of a function. So the concavity of a function is the curvature of a function. When we look at the two graphics that I have on your paper, you'll notice that one of the functions is called concave up. When a function is concave up, the less mathematical term for that is it would hold water if you were to put water onto the function. However, if you're concave down, the graph all the water would fall out. Now mathematically, that of course is not very precise. If you are concave up, that tells you that your first derivative is increasing. And if you were to draw tangent lines, they all fall underneath the curve. If you're concave down, mathematically, what's happening is that your first derivative is decreasing, and all of your tangent lines could actually be drawn on top of the curve. So thinking about concave up, concave down, there are many ways to consider what's happening. Where do the tangent lines fall, and what is happening with that second derivative? So if we're going to test for concavity thinking about derivatives, when your second derivative is positive, your graph is concave up, which means all the tangent lines are below it. If your second derivative is negative, your graph is concave down, and that means that all your tangent lines are going to be above it. Now the place where concavity changes, those are called your inflection points. Where your concavity changes, those are called points of inflection. So points of inflections will occur where your second derivative equals 0 or where your second derivative does not exist. However, it is a key point that the point of inflection occurs where your concavity changes. If your concavity does not change, then you do not have a point of inflection. So what we're going to do for our first example is determine the concavity of the function, and we're also going to determine any points of inflection. Then we're going to make a quick sketch of this function. So for convenience sake, I've given you f of x, f prime of x, f double prime of x. Each of these three functions are going to help us get a good picture of our graph. So let's start with the inflection points. The second derivative, look at that. So I want to know, where does your second derivative equal 0? Or where the second derivative does not exist. So as we look at x squared plus 3, we know that that is never equal to 0. So let's consider where the second derivative does not exist. And those do not exist at x equals 3 and x equals negative 3. However, look at f of x. X equals 3 and x equals negative 3 are not in the domain of f of x. Therefore, they cannot be inflection points of f of x. So not in your domain of f of x. They are not inflection points. Matter of fact, this graph has no inflection points. It's a good way to start with this example. Now, let's take a look at a sign chart to talk about the concavity. Specifically, I'm interested in f double prime of x. I know that the second derivative does not exist at negative 3 and 3 because we have some vertical asymptotes there. The second derivative is going to be positive, negative, and then positive. So that makes this concave up, concave down, and then the graph will be concave up. Notice the abbreviations I'm using. So when we make our statement, f of x is concave up on negative infinity to negative 3. Do not include negative 3. Remember, it's not in your domain. And from 3 to positive infinity. We know that f of x is concave down on negative 3 to 3. So we have information about the concavity. Let's go a little bit backwards now. Let's talk about f of x. Well, remember the interesting features of f of x. F of x tells us where we have vertical asymptotes as well as our horizontal asymptotes. So we know for f of x that we're going to have vertical asymptotes at x equals 3 and x equals negative 3 because that's where your function does not exist. And if you take the limit as x goes to infinity, you will see, of course, that, notice use the correct notation, the limit as x goes to infinity for f of x is 1. So we have a horizontal asymptote at y equals 1, which is good news for us. That's going to help us graph it because now we have the bones of our graph. So let's consider what's going on with f of x in terms of a sign chart. Yes, I'm obsessed with sign charts. Once again, I'm going to put a negative 3 and 3. This sign chart is going to help us figure out if we're going up the asymptotes or down the asymptotes. And as you substitute some values into the left of negative 3, f of x is going to be positive. In between negative 3 and 0, we know that we are negative. And then, of course, to the right of negative 3, we're going to be positive again. So now we know if we're going up the asymptotes or down the asymptotes on either side of 3 and negative 3. All right, what else do we need to know? We should know the zeros of the function. So if we want the zeros, we want to figure out what is f of 0. F of 0 is going to be equal to negative 1 over 9. And the last bit, if I take the function and set it equal to 0, 0 equals your x squared plus 1, which we know does not happen. So we don't consider that intercept. All right, what do we have left? Oh, we have to talk about the first derivative, which is what we were working with earlier. So for the first derivative, what does that tell us? Do you remember? If we figure out where the first derivative equals 0, that will tell us where the function is going to be increasing or decreasing. We also want to consider the asymptotes. So we know that x cannot be negative 3 and x cannot be 3 because of those vertical asymptotes. So if we were to consider a sign chart with negative 3, 0, and 3 on our sign chart, let's see what we get. Substitution tells us that we are positive to the left of negative 3. Then we're going to be positive between negative 3 and 0, negative, then negative. That gives us information. We are increasing, decreasing, and decreasing. All right, so now we have all three parts of f of x, f prime of x, and f double prime of x. They're going to help us graph this function. So how do we put it all together? The first thing you want to do is graph your asymptotes. because those, once again, are the bones of your function. So we have vertical asymptotes at -3, at 3, and we have a horizontal asymptote at 1. Next, we want to put in our zeros of a function, or the intercepts. So for the intercept, we have 0, -1/9. Notice we're just plotting that as best we can. All right, what's next? If we think about where we have relative mins and relative maxes, looking at the first derivative chart, we're increasing, then decreasing. We have a relative max. Let me draw that in. I'll use a different color. At 0, -1/9. After that, perhaps you should consider where we are going to be positive or negative with our concavity. Oh, not yet. Let us consider where we are going up and down the asymptotes. So as you can see, to the left of -3, we're going up. To the right of -3, we're heading downward. Downward on the left of 3, upward on the right. Now, how do we connect this with the horizontal asymptote? The horizontal asymptote, notice when we are on our left side, we probably want to keep the function on the left side and up top. On the right side of the graph, we are on the top part of our function, so let's do the same thing and try to connect what we know. So we want to be concave up and increasing. So fortunately, that makes sense. Once we get to -3, look at the information you have. You want to be concave down and increasing. Let's see if that makes, oh, look, that does seem to make sense. Concave down and increasing. But then I want to be decreasing and staying concave down. Notice how everything seems to fit together. And then I want to be concave up and decreasing. All right, big picture. You're going to plot your asymptotes, then find the intercepts. After that, you want to think about what's happening with the asymptotes and mark what's happening with your asymptotes. And then talk about increasing and concavity together to join all the parts of your graph. So for our second example, we're going to determine the concavity of the function and determine any inflection points of our function. Afterwards, maybe we'll make another sketch. Notice this time I did not give you the second derivative, so we need to practice. So the second derivative is going to require a quotient rule. So what do we have? We have the bottom times the derivative of the top, which is going to be -10, minus the top, so it's positive 10x, times the derivative of the bottom. Remember to use the chain rule. We have times 2x squared plus 4 times 2x, all divided by our second, the bottom, and it is going to be to the 4th power. Now, what I want to point out here, when you find a second derivative of a rational function, your denominator will show up in many of these parts. So let's take a look. Where did it show up? It shows up here, here, and of course in the denominator. So what we're going to do is cancel one factor for each of these parts. So now let's rewrite the function. This is going to be equal to our -10x squared minus 40 plus 2 times 2 times 10 is 40x to the 2nd power, divided by our denominator, x squared plus 4 to the 3rd power. Adding like terms in the numerator give us 30x squared minus 40, divided by x squared plus 4 to the 3rd power. Do a little bit of factoring just to make this easier for yourself. We have 10 times 3x squared minus 4. So from the second derivative, can you see that we have two possible inflection points when we look at 3x squared minus 4? When we set that equal to 0, remember looking for those inflection points, you want to know where the second derivative is equal to 0. That occurs when you have x equal to the square root of 4, which is 2 over root 3. You can rationalize your denominators if you would like, but I don't see the point. We're going to make a second derivative chart. Notice your denominator does not equal 0. F double prime of x has two zeros for us to be concerned about. Negative 2 over root 3 and 2 over root 3. Now, you don't have to know the exact values for 2 over root 3, but I want you to think about this for a minute. Root 3 is near root 4. So that's 2 over root 4. So it's approximately equal to 1 when you are graphing. So keep that in mind when you plot your points. You don't have to write that it's approximately equal to 1, but that might help you. Now, think about positives and negatives. Our second derivative is positive, negative, and positive. So it is increasing. No, it's not. You know better than that. It's not increasing. It is concave up, concave down, concave up. All right, so now we have some information about our concavity. Do we have inflection points? Yes, we do. So let's talk about concavity. F of x, make certain that you state the function. F of x is concave up on, we know from negative infinity to negative 2 over root 3 union 2 root 3 to infinity. F of x is concave down on negative 2 over root 3 to 2 over root 3. From there, do we have inflection points? Notice that the concavity changed at these two values of x. So yes, we do have inflection points. And let's make a statement. We have inflection points. Now, if you cannot solve for those values, it's really okay, but I think we can for this one. Remember, we have inflection points at f of negative 2 over root 3, which equals, put this substitution, 5 over 4 over 3 plus 4. So we can actually simplify this. We get 5 over, and then we'll have 12, 16 over 3. Rewrite this. This is now 15 over 16. All right, so we have two inflection points. Let's list them. Inflection point at negative 2 root 3, comma, 15 over 16. And the other one is going to be 2 over root 3, 15 over 16. And when you graph it, it looks pretty close to 1, 1. All right, now we have all the information about the second derivative. Let's talk about f of x. So we have f of x equals 5 over x squared plus 4. So if we let f of x equal 0, well, it never equals 0, so we don't have to worry about that. But what is f of 0? F of 0 is equal to 5 over 4. So that gives us 1 point that we could plot. Now let's talk about vertical asymptotes. Are there any vertical asymptotes? There are none. Horizontal asymptotes, yes. If we take the limit as x goes to infinity, we're going to get 0. So write in f of x so that you have your limit notation properly written, and then you have 0. Write down y equals 0 as a horizontal asymptote. All right, we've got a lot to put together now. What about increasing and decreasing? So let's look at f prime of x. F prime of x has zeros. Where does it equal 0? at x equals 0. That's easy enough. So we have 0, 0. It has no zeros in the denominator. So when we think about f prime of x using a sign chart, we only need 0. And it will be positive, then negative. So we know that f of x is increasing and then decreasing. Okay, so if we're going to draw that, that is a relative max at 0, 0. That's going to help us draw this graph. Put it all together. Well, unfortunately, the only asymptote that I have is y equals 0. So let's draw that in. I'll draw a little bit slanted so that I can see it. All right, next, we know that we have a value at 0 and 5/4. So we need to plot 0, 5/4. That's a relative max. And I'm going to call this value 1. So 0, 5/4 will put me just a teeny bit higher. So let me erase that and draw it more carefully. Your graphs do need to be drawn as precisely as you possibly can. Inflection points. So if our inflection points are near 1, 1. So near 1, 1, but a little bit lower. Let's call it right here. And then 1 on the right side. There we go. So those will be my inflection points. So put it all together. We know that we are concave up and increasing. So I want to draw something concave up and increasing that's following our asymptote on the left side. Concave up, increasing. Then we switch to concave down, but we stay increasing. So I want to be concave down, staying increasing. There we go. Want to be concave down, decreasing. And then we have to follow that asymptote on the right-hand side. There, nice little graph. So I'm unhappy with the way it's drawn. I'm going to improve it, do a little bit of erasing. Remember what I said, the graphs need to be as precise as you can possibly draw them. All right, you might want to even write IP for your inflection points. And then label your relative max. Okay, that would be example 2. So as you figured out, drawing these graphs takes quite a bit of time and effort. We're going to next graph a trig function. So t of x, I've given you all 3 pieces, t of x, t prime of x, and t double prime of x. Since this exercise is mostly about inflection points, let's start there. Our inflection points occur where your second derivative equals 0 and concavity changes. So if I look at -2 cosine x, set it equal to 0, I know this occurs at x equals pi over 2 and x equals negative pi over 2. Now, it is going to stop at negative pi and pi because we have a domain restriction. That'll make life a little bit easier. So when you make your table of values or sign chart for this one, think about t double prime of x over that entire interval. Put in negative pi, negative pi over 2, then negative pi over 2 has its friend pi over 2 all the way over to pi. Do your substitution to figure out where you are positive and negative. We are positive, then negative, then positive. Now, I would suggest that you choose 0 as your test point first because you should know that the cosine of 0 is 1. Put your negative in when you multiply by -2. All right, but what does that tell us about f of x? F of x is concave up, concave down, concave up. Make that statement. Oops, sorry, I should have used t of x. T of x is concave up from negative pi to negative pi over 2, union pi over 2 to pi. What else do we know? T of x is concave down from, let's see, go from negative pi over 2 to pi over 2. And then do we have inflection points? Yes, we do. And those inflection points occur when we have x equals negative pi over 2 and when x equals pi over 2. Figure out the y values for those using your x plus 2 cosine x. Once you have those 2 points, next we should probably think about the first derivative or even the function. So let's talk about t of x. So t of x, what's happening here? We know that if we take the limit as x goes to infinity of our t of x, we're going to get an oscillating function for the 2 cosine x, but it's oscillating between -1 and 1, and we're going to add x. The answer does go to infinity, so we have an oblique asymptote, and that oblique asymptote is y equals x, which is very cool. If you were to do your substitution, when you substitute in 0, you end up with 2, and if you take your function and set it equal to 0, that's crazy talk, so we're not even going to worry about it. But next, let's look at t prime of x. All right, so what happens with t prime of x? We want to take 1 minus 2 sine of x, set it equal to 0, and look for the zeros. And you know that you have critical numbers at x equals pi over 6 and x equals 5 pi over 6. Taking those critical numbers, so in our sign chart, we're going for t prime of x. We're going to place our critical numbers, pi over 6 and 5 pi over 6. We will then have a positive, negative, and a positive. Remember, we're only going between negative pi and pi, in which case we know that we have a relative max and a relative min in our problem. I'm not going to worry about exactly what those values are because, once again, I'm just sketching. But if you want to draw them and figure them out, you go ahead. All right, let's start placing all the pieces in. Draw in your asymptote. We have y equals x. Plot your important points if you didn't already figure them out. I've written them on the left for you. Let's put in negative pi, and because we have y equals x, this needs to be scaled the same on both the x and the y axis. Plot the points you know. Let's start with 0. 0 goes to 2. All right, so 0, 2 is about here. We know that pi over 6 is going to be a relative max. Pi over 6 is slightly above the 2. Draw in a relative max mark. Then we're going to have 5 pi over 6, and 5 pi over 6 is a relative minimum, around a little bit bigger than 1. So 5 pi over 6 will be a minimum here. When we get to pi, the answer we get is going to be a little bit bigger than what we have. And then at negative pi, the answer is about -5. So our graph comes up above, curves down, and goes up. So this will follow the asymptote if you were to extend the picture, but this is what your graph should look like. Notice the concavity. We have concave up, concave down in the appropriate places, which concavity should switch around negative pi over 2, pi over 2, and pi over 2. All right, so a lot going on here. Notice you can cross oblique asymptotes. I wanted to make that point clear to you as you were looking at this problem. So you figured out that these problems will take a bit of effort. Spend 30 minutes on today's lesson practice, not more than 30. Afterwards, begin the follow-up. You have certain problems that I would like you to try to graph to the best of your ability. You have a fabulous day.